Hi, welcome to the 6th lecture on connectedness, part of topology series. In the last lecture there was some audio problem. I hope you are still able to watch it and understand, and I hope no such thing happens today. The audio quality is reasonably okay. So yesterday what we did was essentially we were sticking to there was only one main result yesterday. If you remember, we proved that the only connected subsets of R are intervals, okay, and that was built out of the fact that the closed and bounded interval AB is connected. Using that, in some sense, we proved the intermediate value theorem of real analysis, and this the connectedness of closed and bounded interval AB are essentially the one and the same. You assume one, we can prove the other. Okay, I hope you enjoyed it. Okay, these are the kind of things which make this kind of in-depth understanding is always good in the long run. If you are worried only about passing your exam, okay, you should not watch my videos. Okay, right. So today I am going to talk about subsets of Rn, R2, etc. Remember, on R2 we already looked at all kind of conic sections, degenerate, non-degenerate, etc. we already looked at. Okay, today essentially I will be looking at in more general case Rn, and I hope you'll find it interesting. Let's go ahead. So whatever I want to do depends upon one basic definition. Suppose I start with Rn. In fact, you can do it in any vector space over R. Okay, and suppose you give me two vectors x and y, and x not equal to y, then I can form a line segment joining x and y. Okay, this is a subset of Rn. Okay, let me just denote by as an interval. Okay, this is set of all elements of the form z in Rn, so that there is a t, so that t lies in the interval 0 1, and z is of the form 1 minus t times x plus t times y. Okay, you can also write it as z equal to x plus t times y minus x, 0 less than equal to 3 less than equal to 1. So how do I visualize that? This is Rn, and I have 2 points x and y. Okay, then this is the line which is joining x to y. Okay, so notice that at t equal to 0, it is x, and t equal to 1 it is y. So this is a line segment, is actually directed line segment, but this is what we call as a line segment. Many of you might have learned this when you learned something about convexity, etc. in your course in Rn or in functional analysis, but you may not know why it's called a line segment. Just for fun, let me do that. So the line joining x and y, okay, this is exactly the same thing, that is x plus t times y minus x, where t is allowed to vary through all of R. Therefore this will be x, this will be y, and this will be the line joining this. Okay, so when t is 0, this is going to be x. When t is 1 and t is negative, it may be here. Okay, and why is it called line? Suppose I take a point z here, okay, in this line segment xy, then z I can write it as z1 z2 zn. That is of the form, okay, x plus x1 extra xn plus t times y1 minus x1 yn minus xn, right? That means there is a t in R now, right? That means, let us look at this. Okay, this is z, therefore zi minus xi, you can see that you take this is going to be t times yi minus xi, right? for each I, comparing component wise, okay, equating components. That says a T must be Zi minus Xi by Yi minus Xi, right? That means this T is common for all I. That means Z1 minus X1 by Y1 minus X1 equal to Z2 minus X2 plus Y2 minus X2 and Zn minus Xn by Yn minus Xn. This is the so-called equation of a line joining 2 points X1, X2, Xn, Y1, Y2, Yn. To make easy, let me look at two things. Suppose let us take point X1, Y1, Z1 and X2, Y2, Z2 in R3. Then the line joining that, point XYZ lies on the line, okay, joining this and joining this, right? That means XYZ must be equal to X1, Y1, Z1 plus T times, okay, Y1 minus X1, Y2 minus X2, Y3 minus X3, right? Therefore X minus X1 equal to T, right, into Y minus Y1 and so on. Y minus Y1 equal to T into, I hope I am writing it correctly, just to make sure, Y1 minus X1, you see that? Please correct me, okay? And Y1 minus Y2, okay, this is the Y minus Y1 will be T times the second coordinate, that is Y2 minus X2, and Z minus Z1 T times Y3 minus X3. Therefore if I eliminate T, therefore T equal to, what do I get? X minus X1 by Y1 minus X1. You can also write it X1 minus Y1 equal to Y minus Y1 by Y1 minus X2 minus Y2. Okay, this is again, I am making a mistake, Y minus Y2. Yeah, and the last one will be Z minus Z1 by X3 minus Y3, X2 minus Y2, X3. Yeah, so this is, you can see, you remove this is the line passing through, equation of a line passing through X1 Y1 Z1 and X2 Y2 Z2. You follow that? That is why we call this as a line segment. Okay, this you can read from my book Linear Algebra, a geometric approach. Pause, review, proceed. Now why is it important? Now comes the thing, right? Now notice that if I give an Rn, again with the standard topology, take 2 points xy, x not equal to y, assume, then look at the line segment. This is a subset of Rn. I claim this is connected. Why? Because let us look at the map 0 1 to Rn given by t going to x plus t times y minus x. Okay, this map is, as we have seen, x1 plus t times y1 minus x1 and so on, xn plus t times yn minus xn, right? So again, as you know, this map, call this as a map f, therefore f1 of fi of t is xi plus t times yi minus xy, right? These are all first degree polynomial in t, therefore they are continuous. Therefore the map f itself is continuous, right? A map from some space to Rn is continuous if only the component functions, if I write f equal to f1, f2, fn, all of them must be continuous. So f is continuous, right? And therefore what is the image f of 0 1? That is precisely the line segment xy, and this is connected, we already know, and this is continuous, we know. Being a continuous image of this is connected. So the first crucial observation is any line segment is connected subset of Rn. Okay, pause, review, proceed. Okay, now we come to the next one. Yeah, suppose I have a subset A of Rn is star shaped if there exists an A in A such that for all x in A, the line segment joining A to X is contained in A. Right? So the natural reason for this star shaped is, I may not draw a picture very nicely. Okay, don't hold me again that. Okay, take any of this point, whatever the point you want, you can take the line segment. Notice that it's not convex, because if I take this point, the line segment joining this is not lying in that. Okay, so this is slightly weaker than convexity, because many of you may have to learn convexity, so I'm just saying that. Okay, so what is star shape? This one. So what do you think I am going to prove now? Can you make a guess? This is a fact 2. Any star shaped subset of Rn is connected. Why is it true? That's again clear. Suppose let f be a continuous function, let A be a star shaped set to R plus R minus 1 subset of R. Right? Let this be continuous. Right? Let take this A. See, there may be many A. Okay, for example, this A will also work. Okay, any A here will actually work. Anyway, let's not worry about. Okay, so let A, I call such an A as a star, A star of A. There may be, as I said, many stars, but let me take only one star of A. Right? Okay, now let X belong to A. Let's look at the line segment AX. What do I know about this? This is connected, and this is also a subset of A. Do you remember that? Therefore, when I restrict F to this line segment, what do I know? This is a constant. Right? Therefore, what do I have? In particular, Fx must be equal to Fa. Have you found out? Yeah. So what do you think I have proved? Give me any x in A. I proved Fx is Fa. What does that mean? That means F is a constant. That means A is connected. Okay. Pause, review, proceed. Many of you will would have heard the word convex set in Rn. Okay, so I say a set A in Rn is convex if and only if for every xy in A, the line segment xy is contained in A. For example, this set is not convex. This is star shape, not convex. Right? So what is the relation between convex set and this? Very interesting thing is, okay, any convex set is star shape. In fact, fix any A in A, then A is star shaped. okay, with respect to the point A, with A as a star. Why? Because I can take, okay, one point to be A, another point to be any Y in A. Then what do I know? This is my X, this is my Y. Then this line segment is contained in A. Therefore it's star shape. Therefore a convex set is a special kind of star shaped set. That is, every element, every point in the convex set is a star, with respect to which the set becomes star shaped. Do you follow that? Therefore convex sets are and conversely, if I start with a set A which is star shaped at each and every point, then it has to be convex set. Okay, try to think, understand. Okay, so what do I have proved? In particular, convex sets are connected, because any convex set is star shaped. We have proved star shaped sets are sets are connected. Therefore convex sets are connected. Right, now let's look at the next thing. What two examples of convex sets? Suppose I start with BAR, okay, maybe closed also, with respect to one of the norms. Okay, our standard norms are, yeah, this is the Euclidean norm, this is the summation norm, and this is the max norm. Okay, with respect to any another norm, but usually we will do this. Right, now the picture is going to look like this. So I have this, I have A, I have this. Right, now this is your center, let's not worry about. Okay, now I want to claim any BAR, any thing is convex. Okay, let me prove or open, this is convex. Why? Let XY belong to BAR. I have to prove the line segment XY is contained in BAR. Yeah, but that's very easy, because start with any point Z here, then Z is of the form 1 minus t times x plus t times y. Of course this is same as x plus t times y minus x, but I have a reason why I want to write like this. Right, so what do I have to prove? I have to prove this line segment is contained in BAR. That means give me any Z, I have to check whether Z is in BAR. Right, that is, so when this is same as saying norm of Z minus A is less than R. Right, but that's very easy, because I can write Z as 1 minus t times x plus t times y, and A also I will write the same way, 1 minus t times A, okay, plus t times A. Okay, this is the only trick. Now this is going to be 1 minus t times x minus A, yeah, plus this is the second term, okay, t times A, this is going to be t times y minus A. But triangle inequality is 1 minus t times, remember 0 less than equal to t less than equal to 1, therefore 1 minus t is non-negative, therefore it comes out, therefore norm of x minus A, and t is again for the same reason, norm of y minus A. But this is less than or, this is less than or, therefore 1 minus t is less than 1 minus t times r plus t times r, which is equal to r. Yeah, so what do you think I have proved? I have proved BR is convex and hence star shaped connected. Okay, pause, review, proceed. Yeah, the second important example is any vector subspace in Rn is connected. In fact, More than that, any translate of that. Connected. Let us go slow, because many of you will have problem with this kind of thing, because linear algebra is algebra. You may not have thought about it geometrically. So the first thing is, see, in Rn we have a natural inner product. This is the usual standard inner product, dot product. Okay, x dot y equal to summation x I y I. Right? Therefore, any vector subspace. Okay, so suppose, keep that in mind, I will come to that later. Suppose V is a vector subspace or Rn. So let x y belong to that, right? Then what do I know? I have to prove, I will prove V is convex. In fact, it's much more, V is convex. That's very easy, because if I take x and y, then I have to prove the line segment xy is contained in V, right? But take any z, it is of the form 1 x plus t times y minus x, or 1 minus t times x plus t times y. Now x is in V, therefore 1 minus tx is in V, and y is in V, therefore V is a vector space, therefore t times y is there, and vector addition, therefore this is in V, right? So what do you think I have proved? I have proved any vector subspace in Rn is convex. The next thing, any translate of a vector subspace is connected. That's very easy, because what is meant by translate? If V is a vector subspace of Rn and fix a point A in Rn, then translate is A plus V, which is same as V plus A, which is set of all points x plus A as x varies over B, right? And why is this connected? That's very easy, because let's look at the map V from Rn to Rn, which is given by x going to x plus A. This is a translation map. This is continuous. Why it's continuous? Because this map is x1 plus a1 xn plus an, right? So this is my f1 of x and f1 of x, and these are all continuous maps, right? Okay, therefore this is continuous. And what is f of V? This is V plus a, right? And we know this is connected and this is continuous, therefore this is connected, therefore any translate is connected. That means, let us look at the picture. Okay, this is my V, this is my V plus a. Okay, this is a vector subspace and this is a translate of that. Okay, that's going to be connected. So in case of R3, what does it mean? I start with any plane. Okay, this plane is given by ax plus by plus cz equal to d. This is going to be connected, because I can take V to be ax, the vector subspace, this one, set of all x, y, z in R3. Okay, this will be vector subspace in R3. Okay, very good. All right, now let's look at few more examples. In Rn, as I said, there is a dot product. With respect to the dot product, I can form what is called n-1 dimensional sphere. For example, in the case of n equal to 3, you have ordinary sphere in R2, which is given by set of all x in Rn, so that x dot x equal to 1. In the case of n equal to 3, it is set of points x, y, z, so that x squared plus y squared plus z squared equal to 1. So this is the sphere sitting S2 sitting in R3. This is called unit sphere. In topology, this is one of the most important examples. This is unit sphere. I want to know whether this is connected. Is the question clear? Yeah. The way we want to do that is something very interesting. How are you going to prove that? Let us look at the sphere. Okay. I may not be able to draw picture very nicely. Okay, please try to bear with me. Okay. Now let's look at the so-called upper half plane. Let me stick to R3 for your explanation, but what I am going to do is true for any n also. So let us look at S2. This is a set of all x, y, z in R3, so that x squared plus y squared plus z squared equal to 1. Yeah. Now let me look at, call this as yes, let me look at what I call upper hemisphere. Closed upper hemisphere. This is, see, this is the thing when z equal to 0. Okay, which is z equal to 0, this is the one. When z equal to 0, what do I get? X squared plus y squared equal to, that's a unit circle in this thing. Do you understand that? Okay. Anything above that. So this is by definition x, y, z in S2, so that z is positive. So similarly I can define S minus, where z is negative. That is this one. So this one, this is S plus, this is S minus. Okay, so you have two things cutting the ball, and notice that they have a point. Oh, sorry, I said close, so I should be very little more careful. Greater than or equal to 0, less than or equal to 0. Okay, so in the case of R2, this is a circle, this is a semicircle, these points are also included, and the lower thing will be like this. This is also included. You follow that? Okay. Now this observation is S plus and similarly S minus. Okay, they are actually homeomorphic, but it's enough if I show continuous images of the unit ball in the plane z equal to 0. Right? What does that mean? Let me look at. So let us look at the plane, in the plane B in R2. Okay, 0, 0, 1. Okay, this set of all. Let me think of this as a point in R3, right? So it's xy in R2, so that x squared plus y squared is less than or equal to 1. This is a closed ball, right? Now we know already this is convex, just now I saw, and hence connected. So if I find a continuous map which maps, let me simply write it as this is an R2, so let me write it as 2 to R3, so that the image of F, okay, equal to S plus, then I know this will be connected and this map should be continuous. Yeah, there is an obvious map. You see that? You give me a U or X, Y in B2 of 0, 1, then XY, where does it go to? It goes to XY. Remember, x squared plus y squared is less than or equal to 1. Therefore 1 minus x squared minus y squared, that is x squared plus y squared, this is greater than or equal to 0, therefore I can take the positive square root of 1 minus x squared minus y squared. Do you follow that? And do you see that this lies in s plus? Because this is a positive square root, and 1 minus x squared minus y squared is non-negative, therefore I can take the unique positive square root, therefore this is a well-defined function, right? Now, and also if you call this x, y, and this is z, x squared plus y squared plus z squared equal to 1, therefore it lies in the sphere, and the third coordinate, z coordinate, is non-negative, therefore it lies in the upper hemisphere. Do all of you understand? And is this map f continuous? Yes, because what are the component maps? f1 of xy is x, f2 of xy is y, and f3 of xy is square root of 1 minus x squared minus y squared. Okay, so all are continuous function, therefore this is a continuous function. You follow that? Therefore for s plus, and similarly the lower hemisphere are connected. Have you understood? What do you think you will define? What should be the map for which will map to s, the lower hemisphere? Remember, the z coordinate must be negative, less than or equal to 0, therefore I will simply take negative square root. Yeah, okay. Therefore I know s is union of s plus union s minus, because you give me x, y, z in s, that is s2, right? Either z is greater than or equal to 0 or less than or equal to 0, therefore it has to be either here or here. It may be in both also when z equal to 0, right? That is the crucial point. Now I know this is connected, and I also know this is connected. Do you remember we have proved a result? If I have two sets A and B which are connected, and A intersection B is not empty, then A union B is connected, right? Do you remember this? After our characterization of connectedness by means of continuous functions to plus or minus 1, this was perhaps the first result I proved. Therefore it follows that this sphere is connected. Go through the proof. These are the things which are usually not done in most of the courses, so I want you to understand these things. So the same proof works in any Sn minus 1 also. Okay, I'll define s plus, where the xn coordinate is set in s minus 1, so that xn is greater than or equal to 0 and less than or equal to 0, right? And let's look at the unit ball in Rn minus 1. Okay, then what will be the map? You start with x1, x2, xn minus 1, map it to x1, xn minus 1, square root of 1 minus x1 squared minus xn minus 1 whole squared. Take the positive square root, this will map into s plus. If I take the negative thing, then it will be s minus. The proof is exactly the same. So we have proved any sphere, okay, this unit sphere is connected. And for that matter, any sphere is also connected. That is, look at the sphere SEA of R, that is set of all x in Rn, so that distance between x and A equal to R. Okay, so I have A, and this is my SEAR. This is my A. This is also connected. Why? Because you can simply say SEAR is nothing else than translate of 0R. So I have a 0R and translate it to A, then you get it. Yeah, and we know the translation is continuous map, and we know, okay, why S0R is connected? That's because, again, that's a continuous image of a map. Let's look at the map from Rn to Rn. X going to R times x. Okay, this is a continuous map, and call this map F. This is continuous. And what is f of 0, 1? This is f of 0 r. Check. Okay, so unit ball goes to r if r is bigger than 1, and goes to r if r is smaller than 1. Okay, and being a continuous image, this is connected, this is a translation, therefore this is connected. Therefore we have proved any sphere. Okay, what is the sphere? Set of all x in Rn so that norm of x minus a equal to r is connected. Okay, so we have seen in Rn vector subspaces are connected, a translator vector subspaces are connected. In particular, if I think of them as a planes in R3 etc., they are going to be connected. And the next important thing is a sphere. We have shown that sphere is also connected. Okay, right, please go through this example. There is one more small example. Let me look at. Suppose I have the unit circle in R2. Okay, and this is a unit circle. Okay, what is unit circle? This is sphere of radius 1 in R2. Okay, right, now what do I want to do is I want to look at there is a subset, okay, E of S, and so that for each P in E I look at that LP, the tangent line at P. Okay, so this is my P, this is a tangent line, and this is my P, this is a tangent line, this may be my P, this may be my tangent line, this may be my P, this may be a tangent line, and so on. Right, now let me look at the set A, which is S union LP, where P is in E. Okay, I want to know whether this is connected. This is exactly the same proof as we showed in a Combs space is connected. Okay, the same argument. Why? We know this is connected and we know each of them is connected, right? You follow that? And therefore if I have a function, continuous function from A to plus or minus 1 subset of R, right, then F is a constant on this, F is a constant on LP. Suppose F is a constant, let us say 1, right? Right, now let's look at, and F is a constant on LP, and remember P belongs to S, therefore the constant is F of P itself, right? You follow that? Therefore F is a constant on the set A, therefore it is connected. Right, so I think this is enough. We will come back with the abstract results about connected spaces in the next lecture. Okay, I hope you all enjoyed, and those of you who had been very regular followers of my lectures on various subjects, you might find it little boring because many things I have to repeat, because I find many of the students have not learned the background BSc material etc., but they are studying topology. They may be watching my videos also, so I wanted to help them so that some of the easy backgrounds I reviewed again. I hope you don't mind. It's always good to review. The more you review, the more confident you become. Okay, thank you very much. We'll meet again.